Alright, so our first topic for this video is conjugacy of Cartan subalgebras in the solvable case, I guess. We'll find out what that exactly is entailing in a minute here. Alright, so start with a theorem. Let L be solvable and our funky E of L as before. Then any two Cartan subalgebras H1 and H2 of L are conjugate under funky E of L. Proof. We go by induction on the dimension of L, with of course the one-dimensional case being trivial, and also the nilpotent case being trivial. So, and we're going to assume that L is not nilpotent. L, due to being solvable, has non-zero abelian ideals. I'm going to choose such an A of smallest possible dimension. Going to set L prime to be L over A. And denote the canonical map phi from L to L over A, the quotient map, by sending x to x prime. By our previous lemma, there exists a sigma prime inside of funky E of L prime, such that it sends the image of one of our H's to the other. Then by previous lemma, we can find some element sigma in funky E of L, such that the previous diagram we drew in the last video commutes. Thus, sigma maps the inverse image, we'll call it K1, the inverse image under phi1 of H1 prime onto K2, being of course phi inverse of H2 prime. We note that both H2 and the image under phi of H1 are Cartan subalgebras of K2. If K2 is smaller dimension than L, then L, by the induction hypothesis, we have taf prime in epsilon of k in funky e of k2 such that taf prime sigma of h1 is h2. But as we saw that funky epsilon k2 is equal to the restriction of the elements of funky epsilon of L on k2 to k2 which is inside this as a set is inside this epsilon L funky of L. So taf sigma of h1 equals h2 for taf in epsilon L with taf restricted to k2 being taf prime, and that gives us our proof in this case. Otherwise, we have that L is equal to k2 because we assumed at one point that k2 was smaller dimension than L, so we could use the induction hypothesis. So L is k2, E equals all of k2 is sigma of k1, so k1 equals k2, and we have that L is equal to h2 plus a, which is then equal to h1 plus a. So we need an explicit automorphism of L. We see that H2 as a Cartan subalgebra is of the form L0 times the adjoint of x for some x in L, as our set A is stable under the adjoint of x A is equal to A0 of the adjoint of x. Direct sum with the A non-zero, essentially, of the adjoint of x. With each summand stable under L, which is H2 plus A, as A is minimal, either A is equal to A not adjoint x, or A is equal to A star of adjoint of x. With the first case, impossible. As it would force A to be inside of H2, which L is equal to H2, contrary to L being nilpotent. But L is not nilpotent. So A is equal to A star, adjoint of X. So A is equal to L star, adjoint of X. As L is equal to H1 plus A, we can write X is equal to Y in H1 plus Z in L star. Well, Z is in A, which is L star adjoint X, with, by previous result, just before, that Z is equal to the adjoint of X on some Z star. With our Z star, Z prime in L star, adjoint of X, as the adjoint of X is invertible, on L star adjoint of X. Since A is abelian, we have that the adjoint of Z prime squared is 0. So exponential of the adjoint of Z prime is the identity in L, is 1 in L plus the adjoint of Z prime. On X, this gives that X minus Z is equal to Y. So H equaling L0 add Y must be a Cartan subalgebra of L. As Y is in H1, H contains H1, since they're both minimal angle, H must equal H1. Thus H1 is conjugate to H2 by the exponential of the adjoint of Z prime. But is this actually in our fancy? It is in fancy E of L, as Z prime can be written as the sum of strongly adjoint nilpotent elements Zi in A, which is equal to L star adjoint X of the adjoint of X, which commute as A is abelian. So the exponential of the adjoint of zi is the product of z, Since they commute, we can split up the exponential into the product of the individuals. It's the exponential of the adjoint of the zi, which all lie in fancy E of L. And that is our proof. Now, so let's move on to the general case from the case where, because we assumed that L was solvable for this. To move to the general case, we need Borel subalgebras. And a Borel subalgebra is, sorry about that, my voice is getting weird, a maximal solvable subalgebra. If any two Borel subalgebras of some L, of a Lie algebra L, are conjugate under fancy E of L, we will get that all Cartan subalgebras from a previous result of L are conjugate. And the important thing here is that this is without L being assumed as solvable. Alright. This brings us to our first lemma. If some B in L is a Borel subalgebra, then B is self-normalizing. So we're going to pick some X in going to be a normalizer in L of B. Then B plus F, our field times X, is a subalgebra of L, which is solvable as the bracket of B plus Fx with itself is going to be B, obviously. So X is inside B as B is maximal. And the second lemma, if the radical of L is not just L itself, then the Borel subalgebras of L are in one-to-one correspondence with those of the semisimple Lie algebra L over rad L L over rad L. As rad of L is solvable, B plus the radical of L is a solvable subalgebra of L for any Borel subalgebra B. i.e. radical of L within B by maximality, and that gives us our lemma immediately. And this, so essentially, this gives us our other case as being the case where, so essentially we can reduce any general case down to the case where L is semi-simple, because the results of the Borel subalgebra on L are going to be the same as the results of the Borel subalgebras on the semi-simplified version of L. So, thus, without loss of generality, let L be semi-simple. Let H be a Cartan subalgebra. Let phi be the root system of L. Relative to our H. I'm going to fix a base of a root system delta. And we're going to set B of delta BH plus the disjoint union for our positive roots of the root spaces, and we're going to let N just be the union of the root spaces of the positive roots. Then we have that B delta is a subalgebra of L with a derived algebra N delta. Furthermore, we have N delta is nilpotent. If X is in some root space, we know that L alpha is going to be positive, a positive root. Then applying the adjoint of X to positive height root vectors, increases their height by at least 1. So we get from this how to make the descending central series go to 0. Thus, B delta is solvable and is actually a Borel subalgebra. KB subalgebra of L, properly including B delta, as K is stable under the adjoint of H, it must include some L alpha for a positive root alpha, negative root alpha, thus K must include the simple algebra S of alpha. So K in this case cannot be solvable. Alright. It comes with another lemma. That's supposed to be a period, not a comma. Let C be semi-simple with Cartan subalgebra H and root system from these phi. For each base delta of our root system, B delta is a Borel subalgebra of L, and it's going to be called standard relative to our Cartan subalgebra. And we want to show that all standard Borel subalgebras of L relative to H are conjugate under fancy E of L. Recall that the reflection of S alpha acting on H can be extended to an inner automorphism I would call taf alpha of L which is, by the way we constructed it, inside fancy E of L. This automorphism we know is going to obviously going to send B of our root system to B of the root system under our new reflection. As the vowel group is generated by reflections, and acts transitively on bases, we see that fancy E of L acts transitively on the standard Borel's relative to H. Well, so up next, we are going to cover conjugacy of Borel subalgebras. The theorem is the Borel subalgebras of a Lie algebra L are all conjugate under our fancy E of L. It comes with an immediate corollary, which is the exact same, except we are working with Cartan subalgebras. And so the proof of the corollary we're going to let H and H prime be Cartan subalgebras of L. Being nilpotent and thus solvable, each must lie in at least one Borel subalgebra I'm going to say B and B prime respectively by the theorem there exists a sigma in epsilon of L such that sigma of B is equal to B prime. Then we see that both sigma on this H and H prime are Cartan subalgebras of B prime, which is solvable, of course. So by a previous theorem, there exists a T prime in epsilon of fancy E of B prime, such that T prime of sigma of H is H prime. but T prime is the restriction of T to as taf prime is the restriction of taf to B prime for some taf in fancy E of L on B prime, which is in fancy E of L. So taf sigma of H is still H prime, but this time taf sigma is in epsilon of L. So once we have the theorem proved, we will get that all Cartan subalgebras are conjugate. So we just need this theorem. We are going to go by induction on the dimension of L, with of course the one-dimensional case being trivial. And by our previous discussion, we can assume that L is semi-simple. Fix a standard Borel subalgebra B relative to some Cartan subalgebra, and we will show any Borel subalgebra B prime is conjugate to B under something in fancy E of L. And if B intersection with B prime is B prime is B by maximality, and we're done. We're done. So we can also use downward induction on the dimension of B intersection of B prime. By assumption, any Borel subalgebra whose intersection with B has a large dimension is already conjugate to B. With any Borel subalgebra with a larger intersection with B being conjugate to B. Okay. First step, we're going to suppose our base case in this induction is that the first case we have the intersection of B and B prime being non-zero. We have a subcase where set M and prime being the potent elements of B intersection of B intersection with B prime is non-zero. Since B is standard, N prime is a subspace. And the derived subalgebra of B intersection B prime consists of nilpotent elements. So of course that means that N prime is an ideal in this intersection. As N prime is not an ideal, in L, so its normalizer K is a proper subalgebra of L. Next, we show that the intersection of B and B prime is properly contained in both B intersection with K and B prime intersection with K. Consider N prime the action of N prime on the quotient of B over the intersection with B and B prime by the adjoint. Each of our x in N prime is nilpotent on this vector space. So by previous theorem, so there must exist a non-zero y plus the intersection killed by all x in N prime, such that x intersection of y is within B intersection B prime with y not in B intersection B prime. But we have that the intersection of x and y is in the derived algebra of B. So is nilpotent. It's not a set. So the bracket of x on y lies within N prime. So y lies within the normalizer in B of N prime, which is B intersection K. With y not in the intersection of B and B prime. And we can do the same the other direction with the other B prime set of B to get it the other way. We also see that both B intersection with K and B prime intersection with K are solvable. Subalgebras we're going to let C and C prime be Borel subalgebra containing B. Borel subalgebras of K containing, including each one respectively. They worded this really weird. I tried to fix it and it didn't work well. And so as K is distinct from L, by induction we have sigma in fancy E of L on K, which is in fancy E of L, such that sigma of C prime is equal to C. As the intersection of B and B prime is a proper non-zero subalgebra of C and C prime, by our second induction hypothesis, we have a TAF in fancy E of L such that TAF of sigma of C prime lies within B. Also, the intersection of B with, okay, this is a really long chain, so I'm going to write it on a new line. The intersection of B with TAF sigma of B prime contains TAF sigma of C prime, intersection TAF sigma of B prime, which contains TAF sigma of the intersection of B prime with K, which is strictly contained in TAF sigma of B intersection B prime, so the former has greater dimension than B intersection is B prime. Once again, by the second induction hypothesis, B is conjugate under fancy E of L to TAF of sigma of B prime. And our second case, where B intersection B prime has no non-zero, no potent elements. That any Borel subalgebra of L contains the nilpotent and semi-simple components of its elements. Thanks for previous results. showing that the intersection of B and B prime, which as from before T, is a Toral subalgebra. Now, say we call that B is a standard Borel subalgebra, so we're going to say that B is equal to the standard Borel subalgebra of some delta. N is is of some delta, and B is H plus N. Since the B bracket with B is N, and the intersection of T and N is 0, the normalizer in B of T is the centralizer in B of T. Let C be a Cartan subalgebra. Now the centralizer in B of T with so C is nilpotent, and T is contained within the normalizer of the centralizer B of T of C, which is just C. If N is an element of N sub B, of the B normalizer in B of C, T is then within T, which is inside of C. So you take the adjoint enough times, T on N is 0. Some K as C is nilpotent. As the adjoint of T is semi-simple, K is 1, and N is within the centralizer in B of T. Thus, we have that normalizer in B of C is the normalizer of the centralizer in B of T of C is C. As C is a nilpotent, self-normalizing subalgebra of B, it is a Cartan subalgebra of B. Which includes T. We know from a previous theorem C is a maximal Toral subalgebra of L conjugate under fancy E of B, hence under fancy E of L to H. So without loss of generality, let T be contained within H. Suppose T is H. As our second, B prime is not equal to H. B prime includes an L alpha with the root space of a negative root. Applying the extended reflection of alpha to B prime yields a Borel subalgebra which we're going to call B double prime, with whose intersection with B includes H and L of negative alpha, the root space of negative alpha. So by our second inductive hypothesis, B delta prime is conjugate to B prime. I mean B, it's already conjugate to B prime. Suppose on the other hand that T is not equal to H either. Now, B prime can centralize T or not. If B prime is contained within the centralizer of T, if B prime centralizes T, by our first induction hypothesis, we see that the dimension of the centralizer in L of T is less than the dimension of L. We are going to use the fact that H is within H centralizes T in L to find a Borel subalgebra B double prime of the centralizer in L T including H and find by induction sigma within fancy epsilon of L on now the centralizer in L of T, which is of course inside of the fancy E of L, and this sigma is going to send B prime onto B double prime. As B double prime is a Borel subalgebra of L including H, it is conjugate to B under fancy E of L by the second induction hypothesis. If our last case, we still have that T is not all of H, and this time B prime is not properly contained within the centralizer in L of t. So B prime does not as a whole centralize t. We may find an eigenvector x in B prime of the adjoint for every element in T, and find an element T inside of T with the bracket of T on X being equal to A of X with A rational and positive. Define S to be H plus the union of L alpha with alpha being the roots such that alpha of t is rational and positive. S is a subalgebra of L and is solvable. We're going to let B double prime be a Borel subalgebra of L, including S. Now, the intersection of B double prime with B prime is contained within T plus f of x, which strictly contains, I said the first one wrong, T, which as we know is the intersection of B prime and B, to the dimension of the intersection of B double prime and B prime is strictly greater than the dimension of B and B intersection with B prime. And similarly, we can get that the dimension of B double prime with B intersect with B is strictly greater than the dimension of B. Oh, the first one was supposed to be B prime. So greater than B prime and B. By the second induction hypothesis, B double prime is conjugate to B, then. And likewise to B prime, and so they're conjugate to each other, obviously. And that's done for our first case. Let's look at our second. That is every possible case where the intersection of B and B prime is non-trivial. Now we're going to look at when the intersection of B and B prime is trivial. The dimension of L is at least the dimension of B plus the dimension of B prime. Since B is standard, the dimension of B is at least half of the dimension of L. So B prime, so essentially it means B prime is going to be like too small to intersect. Take T to be a maximal toral subalgebra. Toral is not an abbreviation, to my knowledge at least, of B prime. If T is 0, B prime is all nilpotent elements. So B prime is nilpotent and self-normalizing, and so is a Cartan subalgebra. But all Cartan subalgebras of L are toral. Thus our T is non-zero. If H0 is a maximal toral subalgebra of L including T, of L including T, B prime has non-zero intersection with any standard Borel subalgebra B double prime relative to H0. Thus B prime is conjugate to B double prime so the dimension of B prime is equal to the dimension of B double prime, which is at least half of the dimension of L, which is a contradiction, because we saw that. So is B, so B prime had to be like smaller. And that's the end of our proof. I will write that just to symbolize it. We see from this, we can attach a numerical invariant, which we can call rank, to a Lie algebra L. As the dimension of a Cartan subalgebra of L. If L is semi-simple, the rank of L is the rank of its root system, of the root system relative to any maximal toral subalgebra. There's another byproduct of this. So we're going to let L be semi-simple, Cartan subalgebra H, and root system capital Phi. And any Borel subalgebra B of L including H is standard. Let sigma of B of Borel subalgebra of a base be B, with our sigma being inside of fancy E of L. Since H and sigma of H are Cartan subalgebras of B, they are conjugate under fancy E of L on B, which is within fancy E of L. So assume, without loss of generality, that sigma leaves H stable. Then for each positive root, sigma of the root space is L of sigma alpha over root sigma alpha. We know that we see that the permutation of roots by sigma preserves sums. So sigma of delta, which is delta prime, is a base of a root system. So B is B of delta prime is standard. What's our next chapter like? The next section is really small. Okay, yeah, the next chapter they're introducing tensor algebras and symmetric algebras, so I think we're gonna have to skip over a lot of that. So I guess I will, just for the sake of making pacing tomorrow, the next video easier, I will finish off this chapter and talk about automorphism groups. It's just a small section anyways. Automorphism groups. Let L be semi-simple with Cartan subalgebra H, root system phi, and base delta. If TAF is an automorphism of L, then for a Borel subalgebra, B, we call B as being B of delta, and of course TAF B is a Borel subalgebra of L, so it is sent back to B by some sigma 1 as a fancy E of L. Now we have that H and sigma 1 TAF of H are Cartan subalgebras of L. So we can find sigma 2 side of E of L on B inside of E of L, sending sigma 1 of TAF of H to H. leaving B invariant. Leaving B invariant. Since now sigma 2 of sigma 1 of TAF preserves both H and B, it induces an automorphism of our root system, which leaves the base invariant, making it a graph automorphism. If you recall, all of our automorphisms acting on a root system are the vowel group automorphisms, can be split into vowel group automorphisms, which permute the elements of the base, and the graph automorphisms, which leave our base intact. But and recall, we only have non-trivial such automorphisms on A sub L, which is our straight length diagram. B and C have a asymmetric, like a 2 map at the end, so those don't have any. DL has a split, we can swap the fork, so DL does E6 is the only one where the branch is in the middle, and the rest, E7 and E8, are asymmetric, and so are F4 and G2. And in each of these cases, we have exactly 2 automorphisms, aside from D4. D4, sorry, my chair is loud, and everything's loud. We always have only 1 non-trivial automorphism unless we're on D4, in which case we have 5 non-trivial automorphisms. Let sigma be such an automorphism of L. Sigma is not quite unique. I guess such is kind of misleading. A corresponding automorphism. Sigma rho is our corresponding automorphism to this thing on L. As rho is not quite unique, we may choose scalars. The scalar, we can pick our scalar choices such that rho of sigma 2 of sigma 1 of t sends each x alpha to c alpha x alpha for positive root on positive roots, which sends y alpha, of course, to c alpha inverse y alpha, and so sends h to h alpha to h alpha. Then TAF differs from an element of the composition of E of L with sigma of L with we're calling that sigma of L being our group of graph automorphisms by a diagonal automorphism, which is the identity on H and scalar multiplication on each root space L alpha. It can be shown diagonal automorphisms are always inner, and actually inside of funky E of L. Also, the product of the automorphisms of L as the inner automorphisms of L times the graph automorphisms of L is semi-direct. So funky E of L is our inner automorphisms of L. And this all comes from Jacobson. And he says there, you can find in Jacobson's book detailed descriptions of the automorphism groups for very simple Lie algebras. So yeah, that's big video today. Next up, they're now only covering the universal enveloping algebra and its interaction with Poincare break-off wit. So yeah, there's a lot of stuff I'm going to have to skip over in this book. I'm going to have to filter through that on my own time later on, but for now we can end it here. Kind of a long one, it's kind of how things pace themselves out today, but yeah, thanks for watching.